Hello students, now we solve question number 33 from the question series of IIT JAM 2024. This question from section B, and this is multiple select question, and the question is, which of the following statements is or are true? The additive group of real numbers is isomorphic to the multiplicative group of positive real numbers. That is option A. The additive group of real numbers. Additive group of real numbers isomorphic. We will check isomorphic to the multiplicative group of positive real numbers. Multiplicative group of positive real numbers. Now we check whether this group and this group are isomorphic. For option B, the multiplicative group of non-zero real numbers is isomorphic to the multiplicative group of non-zero complex numbers. That means option B, multiplicative group of non-zero real numbers and we will check this multiplicative group of non-zero complex numbers. Option C, the additive group of real numbers is isomorphic to the multiplicative group of non-zero complex numbers. Option C. Option C, the additive group of real numbers. Additive group of real numbers is isomorphic to the multiplicative group of non-zero complex numbers. Multiplicative group of non-zero complex number. This group and this group are isomorphic or not. And option D, is the additive group of real numbers is isomorphic to the additive group of rational numbers. That is, we will check the additive group of real numbers. Additive group of real numbers isomorphic or not. Isomorphic or not to the additive group of rational numbers. First we check option C and option D. The additive group of real number, in this group there is no non-identity element is of finite order. That is, there does not exist any element other than identity is of finite order. But in this group there are elements -1, and order of -1 is 2, and in this group one element I belongs to C minus 0, and order of I is equal to 4 because I to the power 4 is equal to 1. So in this group there are some elements are finite order, but in this group there does not exist any element is of finite order. So the additive group of a real number and the multiplicative group of non-zero complex numbers are not isomorphic, so it is not isomorphic. So option C is false. For option D, the additive group of real number, it is uncountable, but the additive group of rational numbers, it is countable. So there does not exist any bijective mapping from R to Q. Therefore, the additive group of real numbers is not isomorphic to the additive group of rational numbers. So option D also false. Now we check option A and option B. Option A, the additive group of real numbers is isomorphic to the multiplicative group of positive real numbers. So let phi additive group of real numbers to multiplicative group of positive real numbers defined by phi of x is equal to e to the power x. So first we check, this is a group homomorphism. So let x y belongs to R plus and phi of x equal to e to the power x, phi of y is equal to e to the power y. So phi of x plus y is equal to e to the power x plus y is equal to e to the power x into e to the power y is equal to phi x into phi y. Therefore phi is a group homomorphism. Therefore phi is a group homomorphism. Now we check, the group homomorphism is injective and surjective. The group homomorphism injective means kernel of phi is equal to identity. Now ker phi is equal to x belongs to R plus such that phi of x equal to the identity element of this group is equal to 1. X belongs to R plus such that phi of x means e to the power x is equal to 1. That means x is equal to 0 only, and this is the identity element of the group R plus. Therefore phi is injective. Now we check phi is surjective. Let y belongs to R plus dot be an element, then there exists an element x belongs to R plus such that phi of x equal to y, or e to the power x equal to y, or x equal to log y. So for every element y belongs to r plus dot, we can find an element log y belongs to r plus. So for every element in the group r plus dot means the positive real numbers, multiplicative group of positive real numbers, we can find the pre-image in the group, the additive group of real numbers. Therefore phi is surjective. Therefore phi is bijective, because phi is injective as well as surjective. So phi is bijective group morphism. Phi is bijective group morphism, and hence phi is an isomorphism. Therefore the additive group of real numbers is isomorphic to the multiplicative group of positive real numbers. Therefore option A is true. For option B, the multiplicative group of non-zero real numbers is isomorphic to the multiplicative group of non-zero complex numbers. That means r minus 0 with respect to multiplication and c minus 0 with respect to multiplication, whether these groups are isomorphic or not. Suppose this group is isomorphic to this group. Since isomorphism is an equivalence relation, so it is symmetric. So if this group is isomorphic to this group, then this group also isomorphic to this group. Suppose phi c minus 0 with respect to multiplication to r minus 0 with respect to multiplication is an isomorphism. Since it is isomorphism and the identity element of the group c minus 0 is 1 and the identity element of the group r minus 0 with respect to multiplication is also 1, so phi of 1 is equal to 1. Now phi of 1 means minus 1 into minus 1 is equal to 1, because minus 1 into minus 1 is equal to 1. Since phi is an isomorphism, it is also a homomorphism. So phi of AB is equal to phi of A into phi of B, because this group also multiplicative group and this group also multiplicative group. This group also multiplicative group, this group also multiplicative group. So phi of 1 is equal to 1 means phi of minus 1 into minus 1 is equal to 1, or phi of minus 1 into phi of minus 1 is equal to 1, or phi of minus 1 whole square is equal to 1, or phi of minus 1 is equal to 1 or minus 1. Since phi is an isomorphism, it is injective and surjective. Since it is injective and phi of 1 is equal to 1, so phi of minus 1 not is equal to 1. So phi of minus 1 is equal to minus 1. Because it is injective, phi of 1 is equal to 1. So phi of minus 1 not is equal to 1. We take phi of minus 1 is equal to minus 1. Now minus 1 is equal to phi of minus 1 is equal to phi of I square is equal to phi of I তার whole square, because phi is a homomorphism. I belongs to C minus 0 and phi of I is the image of I in R minus 0. Therefore phi of I belongs to R minus 0 with respect to multiplication. So phi of I square belongs to R minus 0 with respect to multiplication. Because since phi of I is a real number and the square of a real number must be positive, the square of a real number must be positive, but we see that from here phi of I whole square is equal to minus 1, which is a contradiction, because square of a real number can never negative, so it is a contradiction. Therefore there does not exist an isomorphism phi from the group to the group real number, non-zero real numbers with respect to multiplication. So the group of non-zero real numbers with respect to multiplication is not isomorphic to the group of non-zero complex numbers with respect to multiplication. So option B is also false. Therefore the option A is only correct option. Thank you.